All right, so at the end of that last video, we introduced the idea of upper and lower sums. And again, those are just selecting rectangles in your rectangular approximation method using sample points that are either minima or maxima on the little subintervals that those rectangles are corresponding to. And the idea of a lower sum and an upper sum is kind of more of theoretical importance. For our purposes, we will mostly be dealing with right endpoint or left endpoint rectangular approximation methods. And then later we're going to introduce something called the midpoint method or the midpoint rule. So that's just for reference, really. So now, the technique that we're using, the approximation of an area using all of these rectangles, is it ends up being a lot of arithmetic. It's a lot of, especially when you want to use a lot of rectangles to get a good approximation, there's a lot to write. It's a big sum, typically. So what we're going to be doing here is using summation notation a lot of the time because it's a more compact, more concise notation than writing out all of these terms explicitly. Summation notation is something you should be familiar with from previous courses. Intermediate algebra is typically where you're first introduced to it towards the end of that class when you talk about arithmetic sequences and series and geometric series and things like that. So just a quick refresher, what this notation means. I'm going to write this right here, or reference this right here. It's a big capital sigma. And you have, in this case, it says I equals m down here at the bottom, n up here at the top, and then it has a function appearing here on the right. And what this means is that we're going to be adding up a certain number of terms. The I here is what we call the index, and you'll notice the letter I is showing up here as well with this I right here. So anywhere we see an I in this expression, we're plugging in m, whatever that number m happens to be. So you plug that in, and then you get a term here, and then you add 1 to m, and you plug that in for I and get a new term, and you basically are counting your way up to n. So this here is telling us where our starting point is. This up here is telling us where our end point is. So here is what a right endpoint method for a rectangular approximation of an area would look like in summation notation. It's the sum from I equals 1 to n of f of xi delta x. And writing this out explicitly or expanding that, this would be f of x1 delta x, so it's appearing here, and then we count from 1 up to n. Next would be 2, f of x2 delta x, that appears here. And we keep on going until we get to f of xn delta x, which is here, adding each term that we get along the way. So this is summation notation. Again, I'm not going to do a huge review on it, but we are going to talk about some properties of summations in the next section because we use this notation much more in section 5.2. So let's do this. I want to find an expression for the area under the curve of y equals x plus natural log of x from 3 to 8. So this is the interval that we want to find our area over. And we're not going to evaluate the limit. So again, going back to this, the area is defined to be the limit of this sum of terms here, where these terms represent the areas of these rectangles. And once we apply that limit as n goes to infinity, that approximation becomes exact. So that's what it's referencing when it says do not evaluate the limit. We're going to end up with a limit, but we're not going to even be able to evaluate it right now because we haven't developed the techniques to do this kind of thing yet. So in order to do that, let's first look at what we're going to do this in summation notation. Let's look at what a right endpoint method would look like. I'm going to imagine the x-axis here. 3 to 8, okay? And I'm not going to sketch this function out and draw the rectangles. I'm just going to think about the x-axis and how I'm supposed to split this interval up into n pieces, n equally sized subintervals for my rectangles to rest on. So we came up with a little formula earlier. Delta x, which represents the width of each of those subintervals, is equal to b minus a, which in this case is 8 minus 3. over n, or 5 over n. That's what that comes out to. Okay, now that's going to be the delta x that appears in the summation up here. What does f of xi look like? Well, let's first figure out what x1 looks like. And actually, let's do the general one. What does xi look like? Coming back to this page here, we showed that we can come up with x1, x2, x3, or in general terms, xi, in terms of the left endpoint of the interval that we're finding our area over, plus I times delta x. So what is the left endpoint of our interval? It's 3. That would equal 3 plus I times delta x. Well, if this is delta x, then multiplying that by I would give me 5I over n. Okay? And then what does f of xi look like? Because that's really what's showing up here. Well, I'm just taking this xi and plugging it in to our function. So x plus natural log of x, that's going to look like xi, or 3 plus 5i over n, plus the natural log of xi, which is 3 plus 5i over n. Okay, putting this all in the form of our summation here for our right endpoint method. This is the sum from I equals 1 to n of f of xi, this thing, 3 plus 5i over n, plus the natural log of 3 plus 5i over n, times delta x, which is 5 over n. Okay, no I in this one because it's delta x. This would give me the rectangular approximation to our area with n rectangles. It doesn't become the exact area until we apply the limit as n approaches infinity. So this expression is going to give me the exact area. Now, like we said, we're not going to evaluate this limit, and it's probably scary to just even look at that, right? In the next section, we're going to evaluate the limits for much simpler looking functions, and we're going to use some tricks to do that. And then in section 5.3, we're going to show that you actually never need to evaluate this limit directly, because we're going to come up with a much, much better way for doing this. But let's do one more example like this. This one we're doing in reverse. It says determine a region whose area is determined by the limit below. Do not evaluate the limit. So notice that compare this to what we got up here. Remember, what we're looking at is an expression of this form. It's the sum of f of xi, so a function of xi times delta x. And then also delta x tends to look like a number over n, 5 over n in this case. Well, notice in my summation here, I have a 3 over n. I suspect that that thing right there is delta x, which means that this whole thing should be f of xi. Okay, so let's start with that delta x. Remember, delta x is, in this case, we're saying it's 3 over n, but we define delta x to be b minus a over n, right? So a and b are the endpoints of the interval that I'm finding my area over. So I need to know what a and b are in order to describe this region. Next up, I'm going to come back to that in a little bit. I want to look at this guy right here, f of xi. I'm going to guess that f of x is the square root function because I have the square root of something here, which would tell me that xi is the something inside that radical. That way f of xi would look like the square root of that. So xi looks like 1 plus 3i over n. Now compare that to what we had for xi up here, a constant plus a number times I over n. The constant, that 3, was the left endpoint of my interval. So my constant in this case is 1. I suspect that a is equal to 1. Okay? How do we then find b? Well, b minus a should be equal to 3 according to what we got here. B minus a equals 3, or b minus 1, because we found what a is, equals 3, which would mean that b is equal to 4. Okay, so now I think that my interval that I'm integrating over is the closed interval from 1 to 4. I'm sorry, I used the word integrating. I'm trying to avoid using that. That's the term we're going to use when we define the integral later. So I meant to say the area. We're looking at the area over the interval from 1 to 4. Okay, and then what else do we have here? I have this 3i over n. Well, remember, that's just supposed to look like delta x times I. And notice, in this case, the delta x5 over n was multiplied by I. We said here that delta x was 3 over n, so it makes sense that we're seeing 3 over n times I right there. We now have all the information that we need. We're looking at the area. It says determine a region whose area is determined by the limit below. It's the area below the curve y equals the square root of x over this interval. Okay? That's what we were able to determine from this. All right. Continuing onwards. So we're going to end this section with the first real application of this concept. Now, you might think that this already is an application, finding area, but it turns out that this concept of the area under a curve, where the curve is given by some function, is extremely, extremely useful in a whole lot of different applications. That area actually represents something really, really important in a whole bunch of very different applications, which is why this idea is going to drive what you do throughout most of Calculus 2, and certainly the rest of Calculus 1. The first example we're going to look at is the relationship between velocity and distance. Now, we've already looked at this relationship before, specifically the relationship between position and velocity. We found out that the velocity of a moving particle at time t as a function of t is the derivative of the position function for that particle or object that's moving. But we're going to look at this from a different perspective now. So for this, we want to imagine that we have a particle that's moving, or an object that's moving, and we know from very early on in math that if you have something that is traveling at a constant speed or a constant velocity, then the distance that's traveled over a certain span of time is equal to the velocity times the time. If I'm traveling 60 miles per hour for 3 hours, then 60 times 3, which is 180, is telling me that I traveled 180 miles. But this formula only applies if that velocity is constant, which is rarely the case in reality. If you think about when you drive, you don't keep a constant speed or a constant velocity for very long. You have to brake, you come to stops, you slow down, you speed up. Velocity tends to change over time. So how do we adapt this to the more common case of a velocity that's non-constant? Well, we're going to, rather than derive kind of a general technique right now, we're going to use an example to illustrate this. This example is straight out of your book, and I'm using it because it has nice tables and things. Let's suppose that the odometer on our car is broken and we want to estimate the distance traveled over a 30-second time interval. We take speedometer readings every 5 seconds and record them in this table. So the speedometer is going to tell you your velocity, not your distance traveled. 5-second intervals leading up to a 30-second span of time, and these are the readings that we got from our speedometer. In order to make this a little bit more practical, you're not going to travel several miles in 30 seconds, so it's a little bit better to work in feet in seconds here. If you do a little dimensional analysis, which sounds fancy, but it's something you learn in pre-algebra, or if you have chemistry or physics or something like that, you talk about it, we can convert from miles per hour to feet per second and get this table here. I'm not going to go through those conversions, but they're not hard to do. Okay, so after converting into feet per second, this is our new table that we're going to be working with. Okay, now here's the thing. Let's take a look at the first 5 seconds. Over the course of these 5 seconds, we have a velocity that starts at 25 feet per second and speeds up to 31 feet per second. And who knows what's happening in between, time equals 0 and time equals 5. Maybe it's a constant just increase of velocity from 25 to 31. Maybe somewhere around like 2 seconds we're going as fast as 36 feet per second, and then we actually slow down to 31. We don't really know what's going on there. But here's one thing that we do know. The velocity function is going to be a continuous function. And the reason for that is because one of the characterizations of a continuous function is that small changes in your input will correspond to small changes in your output. Basically, that would mean that there's no jump discontinuities or anything crazy happening like teleportation. We talked about that back in chapter 2. So naturally, a velocity function is going to be continuous. And what the consequence of that is that in a small interval, like a 5-second interval, you can expect your velocity to not change drastically in that interval. And what does that actually mean for us? We can approximate our velocity over this interval by assuming it's constant. So here's what that looks like. If I wanted to approximate the velocity of my car over this interval, I could say that, we're going to just assume that we're traveling a constant 25 feet per second for the first 5 seconds. Even though that's not the case, I'm using 25, the left endpoint of this little subinterval, 0 would be the left endpoint, but the velocity at that time, I could use that to approximate the velocity over that little subinterval. So if I assume that I have a constant velocity for the first 5 seconds of 25 feet per second, then I can estimate the amount of distance traveled in that first 5 seconds using this formula up here. 25 feet per second times 5 seconds equals 125 feet. Okay? Really, the distance will be probably more than that because we appear to be speeding up, but this is going to give us at least a rough estimate. Now, over the next 5 seconds, from 5 to 10, I'm going to do the same thing. We go from 31 to 35 feet per second, but we're going to just approximate that speed as 31 feet per second over that interval. Because if I assume a constant velocity over this next interval, then I can estimate the distance traveled to be 31 times 5, which is 155 feet. We can continue doing that. I can keep finding or keep approximating these speeds over each little 5-second interval with a constant using the left endpoint down here, and just estimating the amount of distance traveled every 5 seconds. Okay? What that's doing is actually creating a rectangular approximation, and here's the reason why. This function right here, the blue curve, is what we're guessing our velocity function looks like. We only have a table of values here, so I can't say exactly what the curve looks like, but I could at least plot the points corresponding to the readings that we do have. That would correspond to these points here. Now notice, what we did first is we assumed that we were traveling 25 feet per second for the first 5 seconds. That would mean that we're approximating our function for the first 5 seconds by a constant function, which looks like a horizontal line. Here's the 25 right here. 25 feet per second for the whole initial 5 seconds. Then how do I calculate distance traveled over that time? Well, it's velocity, which notice 25 feet per second is the velocity. That would be exactly the height of this rectangle here, times time, which is the base of this rectangle. So velocity times time is the area of that rectangle, but it's also my approximation for the distance traveled in that first 5 seconds. And then the next rectangle, 31 is the y-coordinate of this point right here, or really the v-coordinate, because this is the v-axis. That would be the height of that rectangle. 5 is my delta t. It's my amount of time traveled in that, or my amount of time that's elapsed in that next subinterval. but 31 times 5 is both the area of that rectangle and the approximation that I'm using for my distance traveled. Each area, the area of each of these rectangles is my estimate for distance traveled over that 5-minute subinterval. And so adding all of those up gives me an approximation for the total distance traveled. If I used right endpoints instead of left endpoints, this 25 would become a 31, this 31 would become a 35, just because I'm using the right endpoint instead of the left. I could also get a different approximation using my right endpoint method and get 1,210 feet traveled. I could also, if I had more data available, more readings available, let's say we took our speedometer reading every second instead of every 5 seconds, I could get a lot more rectangles using that same approach. You can kind of see from here that if I were able to find the exact area under that curve, which is like taking the limit as the number of rectangles goes to infinity, or the limit as the number of speedometer readings goes to infinity over the course of 30 seconds, I could turn this into an exact answer. So this is a really important example. We'll come back to this in later sections, but the area under our velocity curve from 0 to 30 is going to give us the exact distance traveled in those first 30 seconds. That's how we interpret that. Okay, that's where we're going to leave things off in section 5.1.